This video is going to walk us through the process of pivoting the matrix. That's where we actually apply the simplex method after having found the pivot. So if you look at this matrix, this represents the simplex tableau we might have set up after having expressed a standard maximization problem in matrix form. And let's suppose we've already also found the pivot by identifying the pivot column, which has the largest negative value in the bottom row, and then calculating the test ratios and identifying which row gave us the smallest test ratio. So this 3 surrounded in a box is our pivot. Proceeding from there, we have the following goals. We're going to make the pivot into a 1, and we do that by multiplying or dividing that row by the appropriate value. And then we will take the other entries in the same column, in the pivot column, so this and this, and we're going to make both of those entries into zeros. And we have to do that by adding or subtracting a multiple of the pivot row. So I need to draw attention to this. This is important because you have to use the pivot row when you change the other entries into zeros. You know, just looking at these entries, it looks like it would be really easy, say, to make this into a 0 if we were to add the 10 that's right above it by adding the second row to the third row. But we're not allowed to do that. All of the row operations, when we apply the simplex method, have to involve adding or subtracting a multiple of the pivot row. We cannot use 2 rows that are not the pivot row. We have to involve the pivot row every time. I also want to point out that the first step here, making the pivot into a 1, is not strictly necessary. Sometimes you can get away without doing that. Or sometimes you'll do it, but you'll make one of the other entries a 0 first. But a lot of times we do want to make the pivot into a 1 first because it makes this other step easier. So that process is called pivoting the matrix. After you find the pivot, using it to make the other entries in that column into zeros, and then typically also making the pivot into a 1, that process is called pivoting. Let's see how it works. Our first step will be to make this pivot into a 1. To change a 3 into a 1, I can divide by 3, and performing that as a row operation, I'm going to divide the entire first row by 3. Doing that produces a new matrix, and I continue to draw a box around the position that contains the pivot. So the next step is to make the other entries in that pivot column into zeros. And to do that by adding or subtracting the appropriate multiple of the pivot row. And so now we can see why it might be useful to have a pivot that's a 1. That makes it easier to see what multiple will make things work out the way we need. So for example, in order to make this into a 0, I can add 10, which means I can add 10 times the pivot, which means the right row operation is to add 10 times the pivot row to that third row. So we're going to make this into a 0 if we subtract 10 times the pivot row, and we'll make this into a 0 if we add 10 times the pivot row. But let's do it one step at a time. So our first step was making this into a 0, subtracting 10 times the first row. Let's just see how that works. I have 8, and I'm subtracting 10 of these. So 8 minus 10 is how I get negative 2. Then I have this 10, and I'm subtracting 10 of these. 10 minus 10 gives me 0. I have this 0, and I'm subtracting 10 of these. That's how I get negative 10/3. I have this 1, and I'm subtracting 10 of these. That's how I get 1. This 0 minus 10 of these gives me 0. And this 100 minus 10 sevens is how I get 30. So go through the same process again to make this entry a 0. But this time we're adding 10 of the pivot rows to get the right cancellation. And so again, I started with a value in the third row, and I add 10 of these. Negative 7 plus 10 is how I get 3. Negative 10 plus 10 times 1 gives me 0. 0 plus 10 times 1/3 gives me 10/3. 0 plus 10 times 0 gives me 0. 1 plus 10 times 0 gives me 1. 0 plus 10 times 7 gives me 70. And that's where our new third row came from. So at this point, we've completed our two steps of making the pivot into a 1 and making the other entries in that column zeros. So we've completed a process of pivoting, and we're actually done with the entire simplex method on this example. And the way we know we're done is because when we look at the bottom row, there are no negative numbers left in that bottom row. If there were negative numbers remaining in the bottom row, we'd start the entire pivoting process again, beginning with finding a new pivot. We'll see that in a later example. In this case, since we are done, since we don't see any negative numbers in the bottom row, the question is, well, what's the answer? We were trying to solve a standard maximization problem by going through this process. How can we tell what the answer is from looking at this matrix? So let's go back to the matrix, and these labels at the top here are reminding us where the columns came from. The first column corresponded to coefficients of x in the three equations that led to the rows of this matrix. The second column corresponded to coefficients of y, and so on. So if we take a look at the second column, we can see that there's only one entry that's not 0. The other entries are both 0. Whenever we see a situation like this, we call the variable that corresponds to that column active. So y is active, t is active, and p is active. The other variables are called inactive. That's x and s. Now, as soon as we know a variable is inactive, we know the value for that variable in our final answer will be 0. That's one of our first rules for interpreting the results of the simplex method. So x and s are both inactive. That means x is 0 in our final answer. S is also 0, although it's not normally part of our final answer. There are occasions where we'll need to know the value of s in our final answer, but not for the basic problems we encounter. On the other hand, we do need to know that s is 0, because that's part of what's going to help us find the values for the active variables. So first step is identify the inactive variables and immediately write down that the inactive variables are equal to 0 in our final answer. Next, you take a look at the active variables, and you find their values by looking at the equation that each row represents. So for example, this first row represents an equation, 1x plus 1y plus 1/3 s plus 0t plus 0p equals 7. Now, x and s were both inactive. We already wrote down that they're equal to 0. So if we plug that in, we get this simpler equation, y equals 7. And that's the value of the active variable y. If we used the second row, we would end up being able to evaluate the value of t, but I'm going to skip right over that because I'm really interested in just x and y and p. I already know x and y. We can get p from the last equation, coming from the last row. This row represents the equation 3x plus 0y plus 10/3 s plus 0t plus 1p equals 70. And if we again plug in 0 for each of the inactive variables, we end up with the simpler equation p equals 70. And so now we know the values of x, y, and p. X and y are the inputs that maximize the value of the function that was represented by p. If we plug a 0 in for x and a y in for 7, we end up with a value for p of 70, and that's the best we can do in the standard maximization problem described by the constraints. It turns out that s and t, the slack variables, do have meaning in some application problems, but we'll save discussion of that for a later video.